If society is unable to reduce its dependence on fossil fuels, global temperatures will rise by an estimated 4 degrees Celsius by the end of the century. To prevent this, we must improve renewable energy generation to the point that it can meet the world's growing power demand. One promising solution is solar energy. However, the technology is still too expensive to compete with fossil fuels. To make solar cells more affordable, we can shrink the bulk material to a thin film. This reduces the cost by first, reducing the amount of expensive material used, and second, lowering installation costs due to decreased weight of the modules. However, when we reduce the thickness, a portion of the light is not absorbed, so therefore cannot be used to create electricity. To solve this, we aim to trap light inside of the cell. One way to do this is to turn the light waves across a cell by taking advantage of a material phenomenon called plasmons. Plasmons are waves within a solid formed by the oscillation of electrons around the stationary atoms. Looking back to our solar cell and zooming in a bit, we see that these plasmons have an important effect at the interface between the metal and the silicon. Here, an electromagnetic wave couples to the plasmons in the metal, forming surface plasmon polaritons, or SPPs. By patterning the metal into a nanoscale grating, we can design the cell to most effectively generate these light-trapping SPPs.
From a material science perspective, there are many metals with suitable properties, each with their distinct advantages and disadvantages.
So what material do we use for this grating?
Silver is a good plasmonic material because of its low loss, meaning that SPPs will have a long lifetime. But the wavelength of light where silver has its resonance is not ideal for harvesting light from the sun. Copper is more lossy, but has a resonance closer to the peak of the solar spectrum. Our solution is to alloy these two metals to take advantage of both low loss and a resonance wavelength closer to the peak of the sun spectrum. Before we go any further, I will tell you about the design of our solar cell. From the top down, we have our glass layer, which is used as a substrate for deposition. Next is the indium tin oxide, or ITO, a transparent conductive layer used to collect electrical current. Next are the active layers of the solar cell, which are made of amorphous silicon in our device. These are the layers where the light is absorbed to create free charge carriers. The P, I, and N layers have different concentrations of dopants to create an electric field in the device which drives positive and negative charge carriers in opposite directions. The last layer is our silver-copper alloyed grating, which utilizes SPPs to trap light in the solar cell. It also acts as a back electrical contact. To model the performance of our device, we used two separate techniques.
Our first step was to predict how the dielectric function changes with alloying. We did this by simulating alloys ranging from pure silver to 50% copper and calculating their dielectric function using first principle methods. Each simulation ran on UMD's Deep Thought 2 supercomputer, returned the full dielectric function as a function of energy, which we used to observe how increasing copper content changed both the resonance frequency and the lossiness. Because the true SPP properties are a function of both the silicon and the metal, we then use the dielectric function as input in the next step of our process.
To simulate the performance of this alloy in our solar cell, we use finite difference time domain methods. FDTD solves Maxwell's equations to model how light propagates through different media. We use this to calculate the power of light which is absorbed in our cell. We then plugged the values of power absorbed which we obtained from FDTD into our MATLAB script to calculate the generation rate and quantum efficiency of our cell as a function of wavelength.
Once we determined the composition of the alloy from DFT, we went to the Fab Lab to make it.
We co-sputtered the silver and copper alloys on glass slides using the sputtering system in the UMD Fab Lab. By varying the power ratio between the copper and silver targets, we controlled the composition of the resulting alloy. We deposited several alloys with varied power ratios and analyzed their optical properties, composition, and uniformity using ellipsometry, XPS, and AFM.
We decided that when we fabricate our solar cell, the best way to do this would be upside down, because it would allow us to keep the interfaces in our device smooth. First, we'll spin coat the ITO current collector onto the glass substrate. This is followed by sputtering our PIN amorphous silicon active layers, starting with sputtering the P-type silicon, then the intrinsic silicon, finally the N-type silicon. Next, we'll need to pattern the grading. We'll first spin coat the photoresist, then develop the photoresist using laser interference lithography. Then use reactive ion etching with sulfur hexafluoride plasma to etch into the amorphous silicon. Then we'll remove the remaining photoresist. Lastly, we'll use laser ablation to deposit a uniform composition of the silver-copper alloy, giving us our complete solar cell.
We found that increasing copper content from 12.5% to 37.5% has two prominent effects. First, the growth of an additional lower energy peak in the imaginary part of the dielectric function, and second, increased plasmonic glossiness. We observed good agreement between these trends and the trends from our experimental results. In the future, we would like to conduct additional simulations to predict the excitation of surface plasmopolaritons in a full cell. Thank you to everyone at the University of Maryland who helped make this capstone project possible.